an efficient, reachability-based framework for provably safe autonomous navigation in unknown environments. Autonomous vehicles operating in the real world must navigate through novel, a priori unknown environments using onboard, limited-range sensors. As a vehicle makes progress towards a goal and receives new sensor information about the environment, rigorous safety analysis is critical to ensure that the system's behavior does not lead to dangerous collisions. However, there are several challenges to providing safety guarantees in unknown environments. The first is ensuring safety with respect to unsensed parts of the environment. This safety analysis should also be applicable to a wide variety of real-world sensors. Finally, updating the safety assurances in real time based on new observation poses computational challenges. In this work, we propose a novel, real-time safety analysis method based on Hamilton-Jacobi Reachability that provides strong safety guarantees in unknown environments. Our safety method is planar agnostic and provides guarantees for a variety of real-world mapping sensors. Our framework is based on Hamilton-Jacobi Reachability, which is a safety analysis tool that can be used for nonlinear dynamics and can account for external disturbances. In reachability analysis, we are interested in computing the backwards reachable set, which is the set of all states, such that system trajectories that start from this set can eventually enter an unsafe set of states for some disturbance, even despite the best control effort. The complement of this set is thus the safe set of the vehicle. If the vehicle trajectory starts from this safe set, then there exists a control such that the system will never enter the unsafe set, despite the worst-case disturbance. Moreover, reachability analysis also provides a corresponding safe controller. Before understanding the benefits and drawbacks of reachability for navigation in unknown environments, let's first see how we can compute a backwards reachable set in a little bit more detail. As a running example, let's consider a Turtlebot robot that is navigating through an indoor environment with furniture and clutter. We want to guarantee that the robot does not collide with any obstacles. The first step in HJ reachability analysis is to define a dynamics model for the robot. Here, the model describes the evolution of the Turtlebot's XY position, as well as its velocity and heading and external disturbances dx and dy. Next, we define the set of unsafe states, which is in this case given by the obstacles in the environment. For simplicity, let's take a look at a top view of the same environment. Here, the gray region represents the obstacles in the environment, and the white regions are the free space. Given the set of unsafe states, we define a function, L of x, which is negative inside the obstacle and positive outside. One such function could be the signed distance to the obstacles. Here we see one candidate of L of x, where the sub-zero level of L of x represents the unsafe set. We next define an optimal control problem, whose value function gives us the backwards reachable set. One way to solve this is via the principle of dynamic programming, which, when applied to continuous state and time, results in the Hamilton-Jacobi I6 variational inequality. In this formulation, the Hamiltonian encodes the effect of system dynamics, control, and disturbance on the value. This Hamiltonian is responsible for the value propagation, where the control tries to increase the value or move the system away from unsafe states, and the disturbance moves the system towards the unsafe states. The backwards reachable set can be obtained by value propagation starting from L of x. After convergence, the sub-zero level set of this value function gives us the backwards reachable set. Thus, as long as we are inside the red boundary, our system is safe. Once we have the value function, we can also obtain the optimal controller to keep the system inside of the safe set. Let's project the computed backwards reachable set into the real-world environment we saw earlier. So long as the Turtlebot is inside the red boundary, it is safe. In fact, the robot can apply any controller as long as it is inside the red boundary. However, if the robot applies a control that takes it to the boundary of the unsafe states, then the safety controller can be applied to keep the system collision-free. Unfortunately, as mentioned before, many real-world systems do not have access to maps of the environment a priori to compute these reachable sets. Furthermore, due to the computationally expensive nature of dynamic programming computations, HJ reachability has not been leveraged in settings where the robot does not know the environment beforehand and rather must sense it at runtime. We are going to propose several modifications to the reachability safety framework to overcome these challenges. If we recall our safety challenges from before, let's focus on the first two: safety despite unseen obstacles, and safety for arbitrary sensors. To understand our proposed framework, let's consider a simple example. Here, we simulate a 3D Dubin's car with position x, y, and heading theta that has a front-facing camera. The area marked in blue is sensed initial free space, green is the goal location, and gray is a priori unknown obstacle in the environment. When nothing is known about the environment, we first denote that everything that is unseen to be an obstacle. This allows us to provide safety guarantees despite all of the unseen obstacles. Of course, later on, as the robot moves through the environment, we will take the environment observations into account and update our belief map of the environment accordingly. This initial obstacle map defines our set of unsafe states, from which we can use HJ reachability to compute the backwards reachable set. The vehicle now executes some planned controls, during which it collects new information about the environment. Since it's sensed more free space, the obstacle map is updated, as is the corresponding safe set. Here is the proposed framework in action when the robot is planning using a rapidly exploring random tree. Our framework ensures the safety of the vehicle at all times despite the unseen environment, but does not interfere with the goal-driven behavior of the vehicle. Although we assume that the perception is accurate in the field of view, which is hard to ensure in the real world, we do not have to make any explicit assumptions about the shape of the sensed region and the number or shape of obstacles in the environment. Importantly, this procedure ensures safety despite the unseen parts of the environment and works for a variety of real-world sensors and planners. Now, how do we update the safe set online based on new observations? To mitigate some of the computational challenges, we introduced two novel approaches to computing the backwards reachable set: warm starting and local value function updates. Let's look back at the initial example. Here, gray is the current belief obstacle, and the vehicle is facing forwards. Given this information, we compute a value function, denoted by VOLD. At any given time, after the car has applied some planning control, the vehicle senses only a small additional part of the environment. Consequently, the free space map and the corresponding L of x function only changes by a small amount in the small time horizon. We could recompute the entire value function with the new L of x, but intuitively this should only cause a small change in the safe region. Rather than starting the computation from scratch, we leverage this intuition to warm start the value function computation with the old value function. We can solve the dynamic programming problem once again to obtain a new value function and corresponding safe set. Importantly, warm starting leads to a much faster computation of the backwards reachable set because the value function needs to be updated only for a much smaller number of states that are newly found to be free. At all other states, the value function is already almost accurate and only small refinements are required. We show that this procedure maintains the conservativeness of the safe set. In particular, the obtained safe set through this procedure is a guaranteed under approximation of the true safe set of the vehicle. Although warm starting the value function computation can lead to faster convergence of the value function is still computed over the entire state space. We can leverage the advantages of warm starting by computing and updating the value function only locally at the states for which new information has been obtained since the last value function computation. Recall that only a small number of states was newly sensed to be free. Let's look at the level curves of the previous VOLD value function. Here, wider symbolizes higher value, or safer states, and more orange is lower value, or more unsafe. Our algorithm first starts by finding all the states that are newly discovered to be free, but were previously marked unsafe, here marked in light blue. Since the change in the value of these states will also cause change in the value of the neighboring states, we also consider these for the local value update. The value of all these states is updated using a typical HJI variational inequality for some time step. After the update, we remove all those states whose values haven't changed significantly over the time step, as these states won't cause any change in the value function for any other state. This procedure repeats until convergence. Here we see the algorithm in action for two different vehicle headings, 0 heading and pi/2 heading. Notice how as the algorithm runs, it only updates values for a subset of the state space and eventually converges to a red safe set boundary. Note that this algorithm still maintains the conservatism of the safe set, but provides significant computational advantages. Implemented in MATLAB, the algorithm takes only on average 1 second compared to 51 seconds for the full traditional reachability computation. With this online safe navigation framework, we can now very quickly recompute the set of safe states for arbitrary limited range sensors and for any given planner. To test the proposed approach in hardware, we use a Turtlebot 2 with a mounted stereo RGB camera and showcase how the safety framework can be used to provide assurances around a learning-based planner. Here, the vehicle needs to navigate through a cluttered, indoor environment to a goal position. Since the environment is sensed only through the camera, the dark part of the environment is currently unknown to the robot. To navigate the robot towards the goal, we use a learning-based planner, which uses a convolutional neural network to make planning decisions based on the current observed RGB image. Without the safety controller, the learning-based planner struggles with making sharp turns near the corner and eventually collides into the obstacle, in this case the chair. However, when the learning-based planner is used with the proposed safety framework, the safety controller is able to account for this unsafe situation and safely steer the vehicle away from the obstacle. We show the safe set of the vehicle in red, which is being updated online using the proposed local update method. When the vehicle is on the boundary of the safe set, the safety controller intervenes and steers the system away from the obstacles. Afterwards, the planner takes over and steers the vehicle towards the goal. Our framework can also be used to ensure safety for a variety of learning-based planners, which is typically very challenging to do. To summarize, our contributions are a framework which provides safety in static, unknown environments for a broad class of sensors, planners, and dynamics, an algorithm for online safe set updates from new sensor measurements, simulations of our approach on a variety of sensors and planners on a vehicle with nonlinear dynamics and in the presence of external disturbances, and finally, demonstration in hardware to provide safety around a state-of-the-art learning-based planner which uses only monocular RGB images for planning.